Hi everyone, my name is Born Isaac Berry from Berry Science Lab, and today we're looking at another nice problem about measurability. Let's say we have a function f from some subset of r, omega, to r, and that it's measurable, which means that the preimage of any measurable set is also going to be measurable. Okay, so now let's say we have G from the same domain to R such that G of X works a certain way. If X is in E, G is not equal to F, else G is equal to F. Now let's say the measure of that set E, the Lebesgue measure of that set E is 0, so it's a singleton. So for instance, you can even come up with an example of this very quickly. You can say something like x plus 1 times x plus 2 is f of x, and then g of x could be x plus 1, x plus 2, x plus 3, x plus 4 over x plus 3, x plus 4, and the set E in this case is just 3 and 4. When it's not 3 and 4, these guys cancel out and it just reduces to F. But if it is 3 or 4, this becomes indeterminate. So that's a nice real example. But the big question is G measurable? Well, the requirement for G being measurable is that the preimage of any measurable set M over G is also measurable. Now, if M doesn't contain any elements of E, this forbidden set, where G is not equal to F, then this is satisfied very quickly because G inverse of M is the same thing as F inverse of M. Now, if M intersect E is not the empty set, then here's what we do. We take M and split it up into M intersect E union M without E. And now M without E is just going to follow the same rules. So the measure of G inverse of M is going to be the exact same thing as the measure of G inverse of M intersect E union G inverse of M without E. And this is exactly equivalent to the sum, well, it's only two terms. Yeah. Because these two are disjoint, this is totally equivalent to, but they might not be disjoint after all. So here's what we can say anyway. This is going to be greater than or equal to the measure of this sum. No, this sum is going to be greater than or equal to the measure of their union, because it might be double counting some parts, but that doesn't matter. This is just the exact same as the measure of F inverse M without E, and we know that exists. So what about this set in specific? Well, if you think about it, this has measure 0, which means that it has to be just a bunch of points. So any mapping is any map like G is just going to map this discontinuous discrete set of points to another set of discontinuous points if it's an actual function. So that means that it's not going to map it to anything with positive measure or any measure at all. So the measure of this is going to be 0 because this necessarily has to be one of those single pin sets, a set of just disjoint points. So that means that this is less than or equal to M of F inverse M without E, which means that, therefore, since the measure of something has to be greater than 0, it exists as a real number. Hence, that means that the measure of G inverse M, no matter if M contains elements of E or not, oh, I swapped the cases, no matter if M contains elements of E or not, the measure of G inverse of M, or the preimage of M over G, is always going to exist, which means that G is indeed measurable.
That?
Yeah. Okay.